Pluto is a far-off and stealthy, more humble planet that was once a part of our nearby planetary system. However, recent groundbreaking declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They proposed that this cold world is on a potential collision course with Neptune. But how could this work, and what might be the consequences of such a titanic event? Are we witnessing an intriguing cosmic anomaly, or is there something else to this impending perpetual disaster? Join us as we examine the probable consequences of a Pluto-Neptune collision. Pluto, a former planet that was later reclassified as a dwarf planet, remains a subject of interest and focus in the vast universe, as shown by ongoing estimates from leading experts. Pluto's orbit is dangerously close to Neptune's, and astrophysicists Neil deGrasse Tyson and Michio Kaku have raised the alarm about a potential hazardous impact between these two planets, which could pose a significant risk to Earth. But how is such an event even conceivable? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit, and since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its unusually elliptical shape, meandering widely from the almost round orbits of the major planets. What makes Pluto's orbit even more exceptional is its inclination, which is tilted at 17 degrees to the ecliptic plane. The way Pluto follows its path is considerably more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital plan. One of the most interesting aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the planetary system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to figure out its unique path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit crosses Neptune's. The stability of Pluto's orbit amid these complexities is proof of the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they started and how they pull on each other. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in an intricate manner. The terms non-synchronous vibration, orbital precession, and VZK oscillation are important in this puzzle. According to astrophysicists, what keeps all planets in their orbits is non-synchronous libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from merging. Orbital precession, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, offering an additional layer of protection from potential collisions. Another key factor is the VZK oscillation, named after three researchers who studied how objects move in space. It involves the way three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This gravitational pull influences how they move. In Pluto's case, the VZK oscillation helps explain why its orbit close to the Sun is so irregular. Despite Pluto's path appearing whimsical, this oscillation helps keep it moving smoothly over long periods. The VZK oscillation demonstrates that although things in space may seem turbulent and unpredictable, certain patterns and rules keep everything in balance. These factors help keep Pluto's orbit stable, ensuring that it doesn't crash into Neptune or drift off course. The three-body problem is critical in understanding how these orbits change because of the way space objects pull on each other. Studying this helps us learn more about Pluto, our local planetary system, and even distant worlds and their stars. Mathematical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is actually unstable, with minor deviations in starting conditions leading to huge differences over thousands of years. However, these peculiarities in Pluto's orbit have been found to maintain stability over incredibly long timescales. Monitoring this disruption has been crucial. Later automatic examinations have helped us understand how giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only planet at play. Jupiter's gravity also plays a massive role in stabilizing Pluto's orbit, and Saturn also contributes. These studies show that Jupiter's immense gravity is powerful enough to ensure that Pluto stays on a consistent path for a long time. So perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without running into trouble. These peculiarities are essential in maintaining order and stability in space. Without these elements, the solar system as we know it would be a much more chaotic place. Bodies like Pluto could crash into others or be ejected from their stable orbits, triggering a chain reaction with other celestial bodies. For Pluto, especially with discussions about it possibly crashing into Neptune in the future, understanding its orbit is crucial. This gives a clearer picture of the dynamic nature of the solar system. The case of Pluto shows how even the most seemingly unstable orbits can reach a state of harmony through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and investigation of these phenomena to better understand our place in the universe. Investigating the depths of space often leads us to confront the strange nature of celestial bodies. Moreover, Pluto's orbit is an ideal example of the unpredictability of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions. This is clearly illustrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can significantly alter its long-term orbit. Using computer simulations has been immensely helpful for scientists in figuring out how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune pull on one another. By tweaking small details in the simulations, space researchers can see how even minor changes can greatly affect where Pluto ends up. In the late 1980s, these simulations showed something intriguing about Pluto's orbit. Despite having features like non-synchronous libration and orbital precession to keep it stable, Pluto's orbit can still be erratic and unpredictable. If you start with even a tiny difference in where Pluto is or how fast it's moving, its orbit could end up looking completely different after just a few years. But even with this chaos, Pluto's orbit remains stable over very long periods, like billions of years. This essentially means that Pluto's journey around the Sun has a sort of order to it, even though it seems chaotic at first. Predicting celestial events, especially when they involve erratic orbits like Pluto's, is a huge challenge. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainties. While mathematical models provide excellent tools for understanding and predicting the future paths of celestial bodies, they also highlight the limitations of our predictive abilities. These models depend heavily on the accuracy of initial conditions, and any small mistake or distortion can lead to vastly different results, making precise predictions a daunting task. Moreover, the chaotic nature of planetary orbits like Pluto's reminds us of the ever-changing dynamic nature of the universe. While we've made huge strides in understanding space, Pluto's case reminds us of how much our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly affect the stability and trajectory of other bodies within the system. So why are leading astrophysicists recently raising concerns about a potential crash between Pluto and Neptune? Despite all these complex forces working to prevent such an event, Neil deGrasse Tyson, a prominent astrophysicist and a key figure in promoting cosmology, offers a unique perspective on the mysteries of our solar system, especially the intriguing case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful views on the evolving nature of celestial mechanics and the public's interest in the neglected realms of space. Tyson's position on Pluto's renaming is based on the ever-expanding knowledge of our solar system. He sees the renaming not as a diminishment but as an important adjustment in alignment with our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and change. He views the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. The fascination with these questions keeps space exploration so fascinating. However, despite Tyson's confidence, his thoughts on Pluto's potential impact with Neptune lay out a different picture. His concerns about the future of Pluto's orbit suggest that there might still be some more secrets to uncover. Will Pluto collide with Neptune? Or is this just another moment of confusion in the constantly changing universe of space? Only time and further investigation will tell. For now, we are left with a deeper curiosity about how little we still know about our own solar system. We continue to study these celestial phenomena with the hope of uncovering more of the mysteries that lie beyond. The possibility of a Pluto-Neptune collision raises yet another question about the enigmatic and captivating universe in which we exist. The potential for a collision between Pluto and Neptune raises fascinating issues about the dynamics of the solar system, as it challenges traditional understandings of planetary stability. The idea that two celestial bodies with such incomprehensibly different properties could collide is both unsettling and intriguing, especially considering the current relative strength of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and Neptune is itself a gas giant with a strong gravitational field, the implications of such a collision would be enormous for our understanding of gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential impact, one must first consider the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains a variety of elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere made mostly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is primarily composed of hydrogen, helium, and other lighter elements with a deep, dense atmosphere. A collision between such disparate bodies would drastically affect their structure and behavior, potentially creating an event visible across vast distances. What makes this hypothetical impact particularly captivating is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only factor at play. The presence of Jupiter, the largest planet in the solar system, is another key element. Jupiter's enormous mass, powerful gravitational field, and gravitational pull provide a stabilizing effect on Pluto's orbit, preventing it from straying too far into Neptune's domain. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making it unlikely that a catastrophic event will occur between Pluto and Neptune. The study of Pluto's orbit, as well as its potential interaction with Neptune, underscores the complexity of planetary dynamics in our solar system. The primary concern among astrophysicists like Neil deGrasse Tyson and Michio Kaku is not just the possibility of an eventual collision, but how such an event could be influenced by factors beyond just Pluto and Neptune themselves. The gravitational interplay between these two distant planets is heavily affected by the interactions with the larger, more massive bodies in our solar system, particularly Jupiter and Saturn. Jupiter's gravitational field, with its immense mass, acts as a shield, exerting enough force to prevent Pluto from straying too far into Neptune's orbit. Without Jupiter's stabilizing influence, Pluto could potentially drift into more unpredictable paths, increasing the chances of a collision with Neptune. Saturn's role, while often overshadowed by Jupiter's gravitational dominance, still provides subtle adjustments that help maintain the balance of the outer solar system. These two giants, alongside Neptune, work in tandem to ensure that Pluto's orbit remains predictable despite its eccentricities. Without these forces at play, the solar system's outer reaches could become far more chaotic. This careful balancing act of gravitational forces across multiple planets also highlights the broader implications of planetary evolution over billions of years. These forces have shaped not only the orbits of smaller bodies like Pluto, but have also influenced the general architecture of the entire solar system. For instance, the migration of gas giants like Jupiter and Saturn over cosmic time is believed to have had a substantial impact on the orbits of trans-Neptunian objects like Pluto. These movements may have altered the trajectories of many other bodies in the Kuiper belt, contributing to the relative stability that we observe today. Despite the apparent stability of Pluto's orbit, scientists remain cautious. Mathematical simulations and ongoing observations continually refine our understanding of these celestial mechanics, showing that even minor changes in the position or velocity of a planet can lead to significant shifts in the long term. Although current models predict a stable orbit for Pluto over billions of years, these models are based on the assumption that no other significant forces intervene. As the technology for space observation improves, new discoveries may reveal previously overlooked factors that could influence Pluto's future path, further complicating predictions about its potential collision with Neptune. One of the most fascinating aspects of the Pluto-Neptune relationship is the concept of resonance. This resonance, which dictates that for every 2 orbits Pluto completes around the Sun, Neptune completes 3, is a result of gravitational interactions that prevent these 2 bodies from colliding despite their overlapping orbits. This delicate dance is a perfect example of how seemingly chaotic systems can achieve stability through gravitational interactions. It's a reminder that even in the most distant corners of our solar system, balance is maintained through intricate natural laws that regulate the movement of celestial bodies. However, the future remains uncertain, and any shift in this finely tuned resonance could have significant consequences for Pluto's orbital trajectory, potentially setting the stage for a more dramatic outcome. Astrophysicists also consider the possibility that if Pluto were to experience some sort of external perturbation, whether from a passing star, a close encounter with another planet, or even the gradual shifting of Jupiter and Saturn, it could disrupt the delicate balance that has kept it on its current orbit. Even small changes in the orbital parameters could lead to large-scale shifts over millions of years, potentially increasing the likelihood of a future collision. While such an event is extremely unlikely, the constant movement of celestial bodies means that Pluto's path will never be entirely predictable. The growing interest in the fate of Pluto and its relationship with Neptune not only highlights the complexities of planetary science, but also emphasizes the broader question of how dynamic and ever-changing our solar system truly is. Each new discovery about Pluto, its orbit, and its potential future brings us closer to understanding the long-term behavior of our solar system